In this video, we're going to do an overview of all the things that you probably would have learnt in everything up to year 10 probability. So, some of the things for notations and some definitions. So first one is the outcome of each trial is how many different things you have happening. So in the example there, where you have a spinning wheel, you have 8 different numbers. So the outcome will be one of the 8 numbers. The sample space is all the possible outcomes. You have 8 numbers, so it's 1, 2, 3, 4, 5, 6, 7, 8. Now the weird symbol, I think it's called eta. The way you draw it is you write an E and then you curl it down. You can make it really fancy like that if you want, but that's usually how I draw it. An event is when you want certain outcomes to happen and you will find what the certain outcomes are. So we usually label that with some letter, for example A, or in this case M. The probability of an event is a long proportion, so as in if you do it over a certain amount of time, how many times would it happen? Now, you might notice there's a notation with an N in front, and then you put brackets on what the events are. This N means the number of outcomes for the event. So if you read down here, this means the number of outcomes of A happening over the total. Now just something for you to keep in mind, the total probability, probability should always be between 0 and 1. If you ever get a negative probability, you know you've done something wrong. And secondly, complementary events are the opposites of what would happen. So for example, if A are all the even numbers, then A complement will be all the odd numbers. Or if you like, not even numbers. And they should always add up to 1. Spinning wheel is divided into 8 sectors, each of which is marked with one of the numbers 1 to 8. This wheel is biased. The bias means it's not even. So that the probability of 8 is equal to 0.3, while the other numbers are equiprobable. Now, if you're not sure what that is, break up the word. Equi means equal. Probable, it'll happen with the same probability, so this means equal probability. Okay, calculate the probability of obtaining the number 4. Now we can see that the probability of 8 is 0.3, so what we need to do, we need to find the rest of them. So probability of it not being an 8, because 4 is not an 8, is 0.1 minus 0.3. And then that's 0.7. Now we have 7 numbers left. So that means we take that probability and divide it by 7. So the probability of 4 is 0.1. B. If A is the event, the number obtaining, so if A is any even number obtained, calculate probability of A and probability of A dash. Now, there's a slight trick to this. We know that all the rest of the probabilities are going to be 0.1. So probability of A happening is made up of 2, 4, 6, and 8. However, remember 8 is 0.3. So we have 0.1, we have 1, 2, 3 of these, plus 0.3. So that's 0.6. So make sure you read the question carefully and check carefully on what's happening. So A dash, remember it has to add up to 1, so 1 minus 0.6 gives us A complement, sorry, not A dash, which is then 0.4. Okay, Venn diagrams shows us what's happening with everything that's happening within the set. Now, there are different ways, there are different things you need to be able to read from Venn diagrams. Just a reminder, this means intersection. So in this case, we have two things, that's both occurring. Union is that one. Now union means everything that occurs for, in this case, A and B. Now, all the different sections are shown on the diagrams here. You might want to have a brief read of it, just so that you're familiar with how the diagrams work. So for example, look at this one, A intersection B, that's where they cross over. A union B, it's where, everything for A and B. Complement is everything outside of A. For this one, if you do B complement, then it's everything outside of B. Notice that the intersection is not shaded, because that's still part of A. We want everything outside of A. And then here's a confusing one. A union B complement. If you have a look at the one above, A union B includes all the circles, so A union B complement is everything outside the circles. Now, the notation after it also says A complement intersection B complement. Because if you have a think about it, this is the same as looking at everything outside of A and B. So it's the intersection of A complement and B complement. Now, last thing, the formula below says how A intersection B is related to A union B. Naturally, when we first look at this, we might go, oh, okay, we have A and B, we want everything inside A and B, so then if we add A and add B, we'll get A and B. However, if you notice, as I cross it over, we have A, and I'll use a different color, B, notice that that's crossed over twice. If we add just A and B, we won't actually get A union B. We'll get A union B plus A intersection B. So you actually need to make sure that you subtract it. So don't forget that. Alright, now if two things won't cross over, they're mutually exclusive. Be very, very careful. Mutually exclusives just means that they cannot occur at the same time. That is different to independence. Independence is something else, which I will come to in a second. So the additional formula, because we have no crossover, it's just A probability of A plus probability of B. Also note, because there's no intersection, it must be equal to 0. Alright, from a survey group of 50 people, it was found that in the past month, 30 of the group had made a donation to local charity, 25 had donated to an international charity, and 20 had made donations to both local and international charities. Now just be careful. When you read this, you might notice that it says total of 50, but if you add all three of these, it's more than 50. And that should always be the case. I'll show you the reason why. So we have local charity, and we have international charity. Now make your, I know mine's not very nice, but just make it sufficiently big so you can actually put all this stuff in. Alright, we had 30 for local, 25 for international, and then 20 for both. So let's start with the simple one, put 20 in the middle. Now these numbers actually cater for the ones that have done both. Okay, when it says international, it doesn't specify that it's just international. That means they could have donated for local as well, which then means this: we have 20 for both, and we have 25 for international. If you think about it, there's 25 for international. Some of them, or most of them, would have donated for both, so you must have 5 left for just international. And this will be similar for local. You have 20 for both, 30 for local. That means you should have 10 left. Now, if you have a look at the total numbers in this Venn diagrams, in the circles, you have 20, 10, and 5. When you add those up, you get 35. Hang on, 50 people in total. That must mean we have 15 people left. And this will be our set, which you denote with an epsilon. Okay? Alright, so that's part A. Use appropriate notation, calculate the probability that this person donated to a local charity, but not an international one. So we want the probability of local and also not international. So if you want local but not international, it must just be this section of the circle, which is then 10. This is out of 50, so that's 1 out of 5. Sorry, I'm putting this one, putting in random dots. What is the probability that this person did not make a donation to either charity? So if you have a look, we want the ones that have donated to neither charity, which is outside, which is that number there, so it's 15. Which is then 3 out of 10. Calculate the probability that this person donated to at least one of the two. Now, because they donated to at least one of the 2 charities, what we know is that they must have donated to one or the other at least. So that means they can't have not donated. So the quick way to work that out is 1 minus the probability of them donating to not donating to another charity. That becomes 7 out of 10. Now, just really quickly, you might notice I worked this whole section out with fractions, and on the previous section I worked everything out with decimals. You can do either. However, as a general rule of thumb, you should try and use fractions if possible, because usually they'll be simpler. And we will usually give you questions that can be answered much simpler with fractions rather than decimals. Okay, probability tables, or otherwise known as Carney graphs. Probability tables lets you work out the probabilities as shown here. Just keep one thing in mind. When you add it this way, it should always give you the total. So for example, say that's A. When you add it to the right, that should give you probability of A. If you add it downwards, it should give you a total. B should give you a B. And then on the very corner here, it should add to a 1. Now, this seems to be a really common mistake for people when they first do it. All of these are probabilities. They're not numbers of people. So don't forget to convert them all to probabilities when you do these tables. Alright, we have probability of A being equal to 0.4, probability of B being 0.7, and A intersection B being 0.2. So firstly, write your table. Now, some people might ask, which way around should I do it? Should I do it A first and B? Truthfully, it doesn't really matter. Just make sure you read the correct one. What am I doing? That's not right. B dash. And that's too small, so I'll extend it. Please use a ruler when you do this. Don't do what I just did. Alright, we have probability of A being 0.4, B being 0.7, and A intersection B being 0.2. Now, remember that B's add up across and also down. So 0.2 plus 0.5 gives us 0.7. 0.2 plus 0.2 gives us 0.4. Then remember these also add up to 1 at the end, so that's 0.3, 0.6, and this must be 0.1. Okay, part B. Calculate the probability A complement union, not intersection, union B. Now, remember A union B is probability A complement plus probability of B minus the intersection of B, A complement and intersection of B. Now, because it's the, you might ask, why can't I just add A dash and, A complement and also B? As I mentioned before, when you add them, you're always at the intersection, so you need to subtract it. Then all we have to do is just put in the numbers. That's 0.6. That's 0.7 minus the intersection, which is 0.5. So it's 1.3 minus 0.5, giving us 0.8. Now, this is the most common section where people see that their probability goes over 1. So just double check your numbers, make sure it doesn't go over 1. Or get negative. Right, last little section. Tree diagrams. Remember these show us all the outcomes that can be on there. Also, this one is missing the probabilities, so just make sure you put those on. And if you want to, you can work it out at the end of what the total, what they multiply to, because these scenarios are independent. Lattice diagrams. Lattice diagrams lets us look at what all the different outcomes can be. It might look a little bit useless, but sometimes we can use those to help us look through what happens with the different events. Alright, a four-sided die with faces labeled 1, 2, 3, 4 is rolled at the same time when a coin is tossed. And it tells us to firstly draw a lattice diagram. So I'm going to pick the dice going this way. It's your choice on which one you want. So 1, 2, 3, 4. Again, please use a ruler. Don't do what I'm doing. Okay, B. What is the probability of obtaining a 1 on the die and a tail on the coin? This is where it becomes useful. We want a 1, no tail, which is that one. Because we only have one of these happening, that must be 1 out of, this is a 4 by 2, so that's 8. C. What is the probability? I should fix that a little. Probability of 1 intersection T. Right. What is the probability of the event of obtaining a number which is at least 3 together with a head? So at least 3 starts from here, and we want a head, so it should only be this section. So 3 or greater. And head. That's 2 out of 8, so it's 1 out of 4. Alright, the coin is thrown onto a square sheet of a cardboard of edge. The coin lands with its center inside or on the boundary of the cardboard. Given that the radius is 1.5 centimeters, calculate the probability of a coin landing completely inside the square area. So if we draw the scenario, I'll actually do this up the top. We have a 10 by 10 grid. However, for it to line completely in, we need to make space of 1.5 centimeters this way, 1.5 centimeters this way, so with the other side, like that. Which means we can only get this square area inside of here 7 by 7. So we have an area 7 by 7 out of 10 by 10. So that's 49 out of 100. Just one last little discussion. We're going to talk about independent events and also mutually exclusive. Independent events are events that don't affect each other but can occur at the same time. So just to give you an example, simple one, coin toss, and also a die roll. Mutually exclusive, however, they're events that cannot occur at the same time. So for example, if you're in a race, coming first and second at the same time.